A warm welcome to everyone. Good afternoon. Very happy to have you with us today for our session on the experience of remote monitoring in action. Further ado, I would like to introduce first of all myself and our two lovely speakers of today. My name is Bianca Bonica. I am a partner business development representative at Villari, and together with me I have Diderik Huslache, who's our senior business development manager, and Ems Valentine, our lead project engineer. The session is going to be structured into two parts. First, Diderik will walk you through a short introduction of Villari and our technology, the problem we're solving, and what the technology is actually made of, what it entails. And then in the second part, Ernst is going to talk you through some applications, real applications that we have for our sensor technology. With this, I'm going to give the word to Diderik to start sharing a bit about Villari.
Okay. Hey, good afternoon and welcome. At Villari, we provide a wireless sensor system to monitor steel structures for signs of fatigue stress and cracks. Right? We offer real-time insight and we offer accurate insight in the structural condition of high-stress locations that we monitor locally. It is about steel structures. We are not checking on aluminium or wood. It is only about steel. We are not only telling you when cracks are shown, but also showing you the speed that they are propagating, which is fundamentally different than a lot of other NDT technologies. And this is a breakthrough innovation in our perspective. Right? Usually, NDT tests are usually planned recurring, like every few months or yearly, but leaving the condition of a high-stress location being a black box in between those inspections. That is what our technology resolves. We give you continuous insight in the structural integrity. Fatigue stress is a global issue, right? And we see it not only in cranes, but we see it into bridges, in heavy machinery. And it's happening because they suffer under dynamic forces or cyclic heavy loads, vibrations, and even sometimes due to design flaws. Yeah? Especially assets that are aging, which are coming in the second half of their lifetime, we see cracks appearing. At Villari, we monitor steel highways and railway bridges, harbor cranes, heavy machinery in the steel mills, but we also see fatigue stress happening in its origin in the welding processes. So if you're joining two plates together, you always have some micro inclusions. Yeah, that's just a part of welding, and they will be the starting point of a crack somewhere during its lifetime. So let's take the example of a K-crane, like a ship-to-shore or a ship unloader being used in ports. Roughly after 12 years or 1.5 million cycles, after heavy lifting heavy loads, you will see the first signs of cracks to appear. Once your crane starts aging and coming towards its technical end of life, some of you that are responsible for operations will be challenged. Right? Your operation cost might increase, emergency repairs might happen, more often inspections are required, or you will be faced with unplanned downtime, and sometimes even safety might be a concern. Here in Villari, we have come up with a sensor and analytics platform that is simple to install, robust, wireless, and offers you reporting on demand. Our company is almost like 6 years in business right now, and our companies are among the ministries of infrastructure, like Rijkswaterstaat, ProRail, but also like steel mills like Tata Steel, ArcelorMittal, and ThyssenKrupp. But we're also working with port terminals like DP World and Hutchison, using our patented, certified technology by DNV. To support our rapidly expanding customer base, we also work with a global network of partners. And I'm happy to see one of our partners in Spain joining us. We're also working with an international group of partners like Mistras. Our headquarters is in Delft, which is in the vicinity of the port of Rotterdam, as we are a spin-out of the Technology University of Delft. Asset owners are facing pressure and challenges, and I already mentioned a few of these that asset owners are facing. Aging infrastructures require more frequent inspections, and if you want to keep your asset into operations till the end of the technical design life, you require more inspections. But what about if you're unsure of your port concession, as an example, to be extended, and your crane reaches its end of life? A heavy capex investment might be offset by applying a sensor technology which is sourced on a rental model, like ours. maximum flexibility, and improving the trust in the structural integrity to extend the economic lifetime of your crane. Another example, what we're seeing in the steel factories. If in these days all the investments are being made not anymore in blast furnace like in melt shops there, they are on hold because the investments these days are all in electric arc furnace producing green steel. However, you're still trusting on your girders. They are old, the utilization is still high, and unplanned downtime is a huge burden. Our sensors offer insight reducing unplanned downtime for these environments. Last month, I was at an exhibition and I spoke to a head of operations about his biggest challenge. And he told me, finding skilled, reliable, and qualified resources is a challenge for me, especially the ones doing NDT. His board asked him to assess the dependency on human factor, and he was exploring what resources he could develop to become more autonomous and less dependent on the human factor, while increasing a level of consistency. That was the reason he was looking into smart sensor technology and Internet of Things applications, something that we adhere to with our technology. So how does our technology work? Well, essentially, all steel in the world is being slightly magnetized, which is induced by the Earth magnetic field. In other words, the steel is absorbing this magnetic field, and it is showing really stable over time. When cracking is happening, we will see a change or a redistribution of that standard passive magnetic field due to a redistribution of that magnetic field. What we have found out, and this is what we have patented essentially, is that we have found a correlation between the change of that magnetic field and the force that is happening with the various stage of cracking. So we're not only detecting cracks and the crack propagation, but I think most interestingly, we already see the early signs of plasticity deformation and elasticity changes into the steels, which are the inertial point of a crack. And we are able to show you that real time into a dashboard. This is also the name of this process is passive magnetic flux leakage. In other words, that is also known as the Villari effect, which is also our company is named after. So we are able to show you real time this effect into a dashboard. And I'm going to give you an example how that looks like. But maybe first of that, let's have a look at the sensor. So here you see an overview of an asset. Here a circular tubular section is being welded to a plate. And we're using two types of sensors here being used. We see a short sensor and we see a long sensor. And this long sensor is also flexible. The sensor is being glued to the surface. And I think that is an important advantage. We're using a standard type of glue, a sort of Loctite, gluing the sensor to the surface. It requires only a little bit of cleaning, and we're putting the sensor on the surface. There is no paint removal required as we're measuring through the paint layers. These sensors are being connected to this box that you're seeing over there, which is feeding the sensors 5 years continuously. We can connect up to 20 of these sensors to a single box, which therefore we can also make really long stretches. This sensor box or this transmitter box is connecting over LoRaWAN, which is an industrial Internet of Things protocol, to a gateway, sending the information, the data off to our cloud where we're running the analytics and showing you the results of that real time into a dashboard. That means that the system works independent. It works independent of a standard IT networks. So the advantage is that first, we come on site, do the installation, and the system is immediately in operation. But secondly, since it is independent, there is no risk of cybersecurity for you. The sensors have a broad range of temperature, so we run from -40 to plus 80 degrees, and the sensor system is extremely robust. To install a single sensor costs you like 5 minutes. It is putting some glue on it, holding it to the surface, and after 30 seconds to 2 minutes, the sensor is put on the object. We connect it to the transmitter box, and the sensor is immediately into operation. So what is the information that we're able to show to you? So given the example that we want to see the crack propagation at a specific location. So the example here is we have a crack and we're gluing a sensor in the vicinity of this crack. Once we have glued the sensor to the surface, the sensor requires 2 weeks of calibration. We're taking a sort of baseline of the standard magnetic field and that specific location. After that period, the sensor will come into operation, and here we will show you a green line, means the situation is stable. It is a little bit awkward because, there was already a crack, we're showing you green. But of course, we cannot look hindsight. We can detect the deltas from the moment that we put our sensor on. In the second one, we're showing you yellow. That means we already see the early signs of plastic deformation happening here. So before actually cracking is happening. This is an important milestone. And also you will receive automated alarm notifying your operations team that something is happening. This is then where we make a call and discuss the results and the propagation and the speed and how this information should be considered. On the third one, we see also lines coming into the red, and that will be the time that you're able to see a crack, or at least have a high correlation that you will be able to see a crack. We are able to detect cracks from 1 millimeter onwards. Finally, the crack is fully propagated, all lines in the red, and the light will show horizontally unless the crack is either widening or deepening. When this happens, we roughly can indicate that the total length of the crack is roughly like 4 centimeters. But this is a rough estimate. What we're offering our customers is an online dashboard environment. And in this online environment, you will see immediately in a single overview the status of all your sensors. So giving here the example of a ship-to-shore crane that you're seeing here. A few of those bullets or sensor locations are showing you red, which means that there is something happening there. On the right side, you will find more further information, either details or the live data stream as we were showing in the previous slide. Also, you find here the historic information. On the top right, you see detailed pictures, and here you see actually looking at a flexible sensor that is being mounted on a forestay of a ship-to-shore crane. Here the sensor has 32 zones, and a few of them is actually shown yellow. That means something is happening on the inside of this long sensor actually. What we're seeing here, what we're looking at actually is a crack that is starting from the inside to the outside. To summarize, right, we see use cases in all kinds of industry, whether it is in manufacturing, within steel industries, in infrastructure, offshore, where we suited for non-ATEX certification, or where we're seeing it in port cranes. All steel objects that are prone to heavy stress, cyclic loads, this technology can be used for. Ernst will take it over from me. We'll show you and going over a few use cases that we're working on that we have experienced in the past period.
Yeah, so thank you, Diederik. Now that Diederik has explained what the workings of the sensors are, so how the system detects cracks, I can walk you all through a few practical applications to give some examples of how the system is actually applied in the field. To do that, I'll first make a short distinction between the two main types of application that we see of the system, and that is either a reactive placement or a preventive placement. In the case of a reactive placement, we see people apply the sensors in locations where there is already cracks existing or defects that have been found. In those cases, like the image shown here, the sensors are placed alongside the path along which an existing crack is expected to continue propagating. And this is usually done to give the asset owner some more control and some more insight over what the actual behavior of that crack is. Is it still growing? How fast is it growing? Is it even a fatigue crack, or might it be a defect from welding procedures that is still in the material, but it's not actually growing with usage? But that is done in response to a crack that has been found visually or by NDT to get some more control of that situation. On the other side, we see also a lot of preventive use of the sensors. In these cases, the system is applied in locations where there is no cracks present in the steel yet. Rather, the sensors are placed in places where the cracks are expected to start occurring to be able to flag it early if it does occur. In those cases, we also see a distinction in how is determined where the sensors will be placed. In some cases, that is done based on calculations. So people, for example, have a bridge or a crane, and they have the FEM calculations then to figure out which exact areas of the crane are most sensitive to accumulating that fatigue stress and growing those fatigue cracks towards the end of life. And in that case, the calculations are done, and based on that, a plan is made of where to apply the sensors. On the other hand, what we also see quite often is that the sensor placement is based on empirical evidence or just knowledge of the asset itself. For example, if you have a big steel bridge, there's likely going to be a lot of repetitive details that occur multiple times on a bridge. If at one point in time a crack has occurred in one of those details, it might be chosen to put strips on all of those details just to be able to detect it if the cracks also start to occur there. On the other hand, you might have a series of very similar cranes where some of them have cracked in the past in certain locations, and you decide, okay, let's monitor the same locations on different cranes we have, once again, to be there very early once these cracks start to occur. Knowing that, I will lead you guys through a few examples that we have of practical applications. So the first one we have here is a very good example of a reactive usage of our sensors. In this specific case, in a very big steel production site, cracks were found during NDT processes on the structure that held an operator cabin onto an EOT crane. In this case, an EOT crane with a very high operational pressure, meaning that a repair was scheduled for this location, but the repair was scheduled 6 months later than the point at which the cracks were found, because that was the most efficient time, the most cost optimal time to do that repair. In the meantime, to ensure that the crane was still safe to use and the cracks wouldn't really have a lot of structural risk in the meantime, the sensors were brought in and they were put on all of the existing cracks to detect whether or not those cracks were growing and how rapidly they were growing. In this case, because it was only 16 of the sensors, we managed to squeeze the installation into a long shift change. So within 1 or 2 hours, we managed to install the entire system, and after which we were able to report back to this asset owner what was happening there. In this case, after only 1 or 2 months, we noticed a lot of very rapid crack growth on these sensors. In some cases, to the point I would say we have stopped seeing these cracks because they've grown so fast, so far, they have grown out of the range of our sensors again already. This is worrying. This asset owner then stopped the crane, went back onto the crane to do an additional inspection, and indeed found that all of these cracks were growing at a very worrying rate, to the point where they could no longer vouch for the safe operation of the crane. So they stopped the crane, took it out of operation, and did repairs at an earlier point. In this case, just greatly increasing the operator safety for the people working in that crane and managing to flag a potential accident quite early. Another example I can give of some reactive placement of the sensor system is one that we have been working on for quite a while on a very specific large span steel highway bridge. In this case, a crack was determined during routine NDT operations after 5 years after the asset had been produced. In one of the primary steel members in a very hard to access locations, cracks were found, and to say it was 5 years after production, so they really were not expecting to find these cracks yet. Calculations were done on what the cost would be and what the impact would be to have these locations repaired, and they turned out to be massive, mainly because due to the specific location and the hard accessibility, the entire highway would have been closed for several days to be able to perform this repair. Therefore, of course, there's a high motivation to try to defer that repair cost and keep the situation in control in different means. In this case, that would mean a very frequent inspection of a very difficult to access location, which would also be a very costly endeavor. So that's where we were brought in, and we applied our sensor system both to these existing cracks in a reactive fashion, but also to the same structural members a bit over on the bridge, so the repeated details there, to be able to flag any newly occurring crack growth there very early. The system was installed, calibrated, and after a long period of monitoring, I think now about 2 years, we are still not seeing any continuing crack growth from this location, which has now led this asset owner to also believe that these cracks were mainly due to defects in the manufacturing and not necessarily due to fatigue stress already causing this damage in the bridge. Right now, we are still monitoring, and the customer is also still inspecting, but at a very much lower frequency than what they would have done otherwise, helping them defer a very large repair cost, but also indeed giving them more peace of mind, more control in the long periods between those inspection intervals. Then, as we see those as examples of a reactive placement of the system. I'll go through some examples now of the preventive placement. First example here would be a ship-to-shore crane at the quayside of one of our customers that they procured, and within 3 years after it being in operation, it already showing significant cracks and near failures of some structural members. To keep in mind, ship-to-shore cranes are typically designed to have about 25 to 30 operational years. In years was, of course, way too early, and in this case also still within warranty. So the first cracks that were found in this crane were repaired by the manufacturer under warranty. But again, after about a month, I think, or about a year after repairs, they were cracking again and they were being repaired again. But each time that happened, it was costing several weeks of downtime for these cranes, for the operator, costing them a lot of money. So after the last round of repairs had been done and some reinforcements were placed as well, our sensor system was applied to both the repaired members but also to the areas around it to see is anything new going to start happening here. In this case, which even for us is slightly unlikely, but within a week we were already seeing some very strong signs of crack growth occurring. We flagged this to the customer, but also with a message: we're seeing crack growth, but we're seeing it very rapidly and at very short intervals. In this case, after doing that reporting for a while, they did an additional inspection. They found very minor cracks right next to the sensor strips where we're seeing this activity. But more importantly, they were able to relay this information of when we were seeing these very high bursts of crack growth back to some very specific occurrences in the way they were operating this crane. So to actual events happening to the crane that they could then relate to them causing the crack growth to happen. With that knowledge and with that information, they were then able to go back to the drawing board together with the manufacturer and plan the repairs as reinforcements to ensure that that specific behavior would no longer cause these cracks to occur in these locations. And now after that, we are still continuing to monitor them, and this time so far without continuing crack growth. And then lastly, I have another example of a preventive placement that we've seen used in another very large steel production site. The steel production site in this very specific hole, which was about 40 years, 12 EOT cranes, like heavyweight EOT cranes, were acquired at the same time and taken into operation about 40 years ago. They've been designed for a bit less than that, for a bit less cycles than that. So a few years ago, they ran into the issue where technically they were ending their design end of life. But because there were so many cranes and they weren't really seeing many defects yet, the decision was made to do a very in-depth study and do the FEM analysis to figure out if this crane will start cracking, if we see the fatigue damage occur, where is it most likely to start. At that point, they figured out they had a few very intense hotspot locations where these cracks were expected to occur, that were also in locations that were very hard to access, and also in locations that if they cracked, they would lead to a critical failure of the crane. So in response, they thought if we have to continuously monitor that, do very frequent inspections, due to how hard these locations are to access, that is not a business case we can make. That is difficult for us. It might be better to then do the investment. At that point, they estimated about 5 million per crane to be replaced. Or we can start inspecting these locations at a slightly lower frequency and monitor them in the meantime to make sure that these cracks are not starting to happen there. So we were able to go in there, perform the inspections with about 3 or 4 cranes we managed to do per single day of installing the sensors. And after that, we are now monitoring that location for about 2 or 3 years. And in all of the locations, we are still not seeing that crack growth happening yet. But at this point, that has given this operator the safety that in between those inspections, there's not suddenly something happening. We know for sure that those locations, there's no crack growth occurring, and has given them the possibility to keep postponing that very big capex investment to have to replace those cranes to keep this site in operation.